Okay, Mr. Samuels here with the continuation of our lesson on gas laws. First thing you need to know is something called STP. STP stands for standard temperature and pressure. Standard temperature is 273 Kelvin, and standard pressure is the same as atmospheric pressure. If you look earlier in your gas laws notes, you'll see that's 1 atmosphere, 101 kilopascals, or 760 millimeters of mercury. So if you see STP or any of these, this is what you would write. So now that we know that, let's move forward and talk about the combined gas law. So far we've only been changing two variables at a time. And if all three are changing, we're going to need one equation to unite them all. It looks like this. P1V1 over T1 equals P2V2 over T2. And the temperature, of course, must be in Kelvin. So take a look at this real quick. You might be saying, oh no, another equation. Well, guess what? This one you're going to like because it actually makes your life easier. Let's say, for example, temperature's not changing. Temperature's constant. Well, then T1 equals T2. They're going to cancel out. And look what we're left with. P1V1 equals P2V2. Boyle's law. For example, if in another case pressure's not changing, you can cancel those out, and you get V1 over T1 equals V2 over T2. Dun 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 dun. Charles' law. So really, so far, you only have to learn this equation. It's got all the others covered. Now, there's a lot of variables here, so when we do an example, let's be very careful paying attention to our list. For example, a sample of carbon dioxide occupies 68 milliliters at 30 degrees Celsius and 725 millimeters of mercury. What would the volume be at STP? So let's take a look at our list. P1, 725 millimeters of mercury. V1, 68 milliliters. Now, our new pressure, I don't see one, but remember, STP means standard temperature and pressure. So if the first one is in millimeters of mercury, then we're going to use millimeters of mercury for our P2, our standard pressure. If they gave you a P1 in atmospheres, we'd use 1 atmosphere, etc. Okay, V2 is the variable we're looking for, and let's see, where's the second temperature? Oh, that's right, STP. So standard temperature is 273 Kelvin. And our starting temperature, of course, 30 degrees Celsius, we convert to Kelvin. Okay, now the algebra here gets a little messy. I didn't write it all out, but I hope you can figure this out. If we're looking for V2, we need to get rid of P2 and T2. So divide both sides by P2, boom, and multiply both sides by T2. If you need help with that, ask someone in your team. I'm sure they can help you with the algebra. Now, this is why I say do the algebra first, because if you plug all this stuff in first and then try to do this, your life is going to be miserable. So, now that we have this form, let's plug our numbers in. P1 on top comes straight off our list, V1, T2, all that. Make sure you get them in right. And notice everything cancels except for milliliters, because milliliters is a unit of volume. That's what we're looking for. Plug all that stuff in. You should get 58.4 milliliters. And I should also mention, if you're in honors, this is exactly 760. So that's actually 3 significant figures there. Technically, I guess your volume here is 68 milliliters, so you'd round that to 2 sig figs if you're in honors. All right, moving right along. There's a practice problem. You can try that before moving on and seeing the answer, but I have the solution below. You can pause. Otherwise, if you're just taking the notes, don't write this down yet. You can go over that later. Oh, here's a few practice, actually. Okay, but more importantly, let's move on to the ideal gas law. The ideal gas law, PV equals nRT. That's how I try to remember it with the rhythm. PV equals nRT. PV equals nRT. You know what all of these mean except for N and R. N stands for number of moles and number of moles. Remember, M is already taken, so N is moles. And then R is this thing called the universal gas constant. It's got this crazy set of units. R is 0.0821 liters atmospheres over moles Kelvin. That's a lot to memorize, so I usually come up with an acronym. I've heard some students say things like ladies are more kind. I was a weird person in high school, so I came up with something bizarre like llamas ate my kids. Whatever works for you. Just know that this time, in the ideal gas law, nothing is changing. We don't have any ones or twos. What we have is every variable that affects the gases, and so therefore, using this constant, this is one just that comes from experiment. We found this number makes the equation work, this gas constant. We can find out any of our missing variable as long as we have the other three. Okay, so let's look at, oh, and of course temperature must be in Kelvin. Let's look at an example with this. What pressure must be applied to 4 moles of gas to keep it at a volume of 40 liters at 60 degrees Celsius? So, on our list, PV equals nRT, we've got our pressures, what we're trying to find. But notice there's no second volume, no second temperature. And also, since the fact that we have moles, that's a huge hint. We're going to be using the ideal gas law. So, plug all this information in. If we solve PV equals nRT, if we're trying to find pressure, divide both sides by volume, and that will get you this form of the equation here. Sorry, this is just part of our list. It should have been more over here. At any rate, so now let's plug those in to this equation here. N is 4 moles. R is all that business we said before. 0.0821. Llamas ate my kids. Temperature, 333 Kelvin. And then on bottom, we're going to put our volume, 40 liters. Now watch this. Here's why R has all those crazy units. Everything's going to cancel except what you're looking for. Notice moles cancel. Kelvin cancels and liters cancels, so all that's remaining is atmospheres, which is a unit of pressure. Dun, 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 dun. And that's what we wanted. So, gosh, I'm sorry if that's not coming up on your screen properly. It says 2.73 atmospheres. Oh, there we go. And that is your pressure. If we are in honors, then we're probably just going to round that to 1 sig fig here, since these only have one significant figure, so you'd say 3 atmospheres. Everybody else, remember, round to 3 sig figs at least. Okay, so if you are in college prep, you can stop the video now, do some practice or work on your homework. For the rest, for honors, there is still one more piece. So try a practice problem before looking at the answer. I want to put it up so you can pause the video. Okay, now once you've got that taken care of, we can move on and talk about one last gas law for honors, and that is Dalton's law of partial pressures. So you may remember this guy. He had this, little contribution to science. Came up with this, theory about these atoms, kind of important to chemistry. At any rate, so after his work on atoms, he moved on to exploring lots of other things, and he came up with his law of partial pressures. What this is for a mixture of gases. Now, what he found is that each gas contributes equally to the pressure. So if you have air, for example, it's mostly nitrogen, and so therefore nitrogen is going to contribute most of the pressure of the balloon, or in a balloon filled with air. So let's look at these variables here. N1 stands for the number of moles of whatever the gas in question is. P1 is the partial pressure. I would make that note on your notes here. Put arrows towards these: partial pressure, number of moles. This is total number of moles, and this is total pressure. So you might need to pause to write that stuff down. But that is Dalton's law of partial pressures. Let's see it in action. For example, a sample of gas contains 2.5 moles of nitrogen and 1.5 moles of oxygen at a total pressure of 3 atmospheres. Find the partial pressure of nitrogen. So this is kind of similar to air, a mixture of mostly nitrogen and oxygen. Let's take a look. How do you find the total number of moles, NT? Well, you just add up all the partial pressure, or all the partial number of moles. So 2.5 moles of nitrogen, 1.5 moles of oxygen gives us 4 total moles. Our total pressure is given 3 atmospheres. And so now we just want to try to find the partial pressure. But instead of putting N1, okay, and P1, I'm just going to put the substance it's asking about, nitrogen. So the number of moles of nitrogen instead of N1, the partial pressure of nitrogen instead of P1. Okay, doing the algebra there, if we multiply both sides by PT, we're going to get this equation here. Plug in your values, and you're going to get, please forgive the sig figs, you should probably have 2 here, 1.9 atmospheres. Now, here's the deal. Oh, and oops, moles, of course, would cancel. Now, I want you to see how this makes sense. If we have mostly nitrogen, a little more than half nitrogen, in our mixture of air here, then that means that out of our 3 atmospheres of pressure that this sample of gas, this mixture of gases is exerting, then more than half should come from nitrogen. Hey, look at that. It did. Okay, so that is Dalton's law of partial pressures.